Hi, everyone. I hope you are all able to take a nice break. Now we'll be having Andre Kozma presenting using Python and 3D depth sensing for advanced machine vision applications. We'll have about 5 to 10 minutes at the end for Q&A again. So if you have any questions at that time, just post it in the Q&A tab or raise your hand. Take it away, Andre.
Thank you. So, hey guys, and welcome to this session. I'm Andre. I'm an engineering manager with Analog Devices. And in today's session, I'm going to talk a bit about developing machine vision applications in Python using data from 3D depth sensors. So, before we start, let's take a quick look at the agenda. So, I'm going to start by introducing 3D depth sensing and tell you a bit about how it works, what is it good for, and what are some of the available development systems that ADI has to offer. Then we'll take a look at the Analog Devices open source time-of-flight SDK. We'll dive a bit into the architecture, the Python API that we have for this SDK, and some example applications which are available. And then we'll look at some machine vision applications with Python, targeting people detection, human pose estimation, and volumetric measurement. So I'll start by just giving you a quick overview of what 3D depth sensing is and how it works. So basically, the way it works is that we do have a light source, which is an infrared laser, which emits pulses of light. The light basically goes and reflects back from objects in the scene. And there's a receiver which measures the time it takes for the light to be reflected from the objects in the scene. And basically this gives us information about the distance to all the objects in the scene in front of the sensor. Basically here in this picture we can see an image of a depth map. So I know that this looks like a heat map, but what it actually is, it's a depth map where the warm colors represent points which are closer to the camera and to the sensor, and the colder colors represent points which are further away from the camera. So basically we get a VGA image in this case, where each pixel in the image represents the distance to the corresponding point in the scene. So basically this acts pretty much like a 2D camera. So it gives us an image which makes sense, but each point in the image is a distance to the points in the scene. So what is this good for? So there are many applications, like autonomous vehicles in warehouses. So it's basically robots that need to navigate in a warehouse or in a factory, and they need to see the different objects. They need to understand the scene, and they need to make sure that they don't bump into anything that's in front of them. It can be used for 3D scanning of boxes. So basically this can be useful for logistics applications, where you would have your FedEx guy, for example, coming and scanning the dimensions of the box before he puts it in the truck. And that gets communicated to a server somewhere so that they can manage the space in their plane or ship or whatever they are using to ship the boxes. It can be used for other things like people counting, Face ID for control zone access, or gesture control. So these are some example applications where 3D cameras can come in handy, and they bring some advantages compared to traditional 2D vision systems. So ADI has, I guess, complete solutions for 3D depth sensing. I'm not going to go into those. I just want to give you like a quick overview of the different development and time-of-flight modules and smart cameras that we have, which basically are designed to connect. So for example, the development systems and the time-of-flight modules, they are designed to connect to different processor boards like a Raspberry Pi or boards from NVIDIA or Rockchip or different other manufacturers. in order to be able to get the data from the time of flight camera and do further image processing to implement different machine vision algorithms. And they also have this concept of the smart cameras, which basically combine a 3D and a 2D sensor with AI-capable processors in order to be able to provide edge processing for machine vision applications. So going further, I'll talk a bit about the open source SDK that we have for our 3D depth sensing solutions. And I'll tell you about a bit I guess the way the SDK is structured, the architecture of the SDK, and the Python API that we have on top of the SDK. So as I said previously, the SDK is open source. It's provided under a BSD3 license so that anyone can use it as is, integrate it in their product, do prototyping with it. So basically, it's a complete open source implementation that can be freely used by anyone who's interested. It has support for multiple OSs like Linux, Windows, Mac, different connectivity options like MIPI for connection to the camera directly over like the standard MIPI interface, or USB Ethernet for connecting to a PC and running different algorithms on the PC. It has wrappers for different popular software frameworks and languages like OpenCV, C++, Python, of course, Open3D, MATLAB, and RobotOS. And it has different API levels. So it has a low-level API, which provides hardware control, configuration, data capture management, calibration. So it's basically direct access to the different hardware components for configuration and control. So this is targeted to framework and tool developers and advanced researchers. We have a high-level API, which is for application developers, system engineers, or algorithm developers. And we do have bindings which sit on top of each of these APIs so that different people can use their preferred programming language when interacting with the hardware through the SDK. So here's just a quick overview of the software infrastructure and how everything looks like. So starting from the bottom, we have the hardware here, and then we have an embedded system which is running Linux. And in Linux, there's a v4L2 kernel driver which talks to the hardware via MIPI for video streaming, and SPI or R2/3 for hardware control. And then the SDK talks to the driver directly. And there's also the option to connect the embedded system to a PC, where we run the same SDK, but with a different backend, which can be either a network backend or a USB backend. So this is kind of the high-level architecture of the SDK. And what's nice about this is that it kind of provides all the tools for the different development stages. So for example, in the initial stages, people are doing like prototyping, algorithm development, application development, and it's much easier to do those kind of things on a PC. So it's definitely preferred to use like the network or the USB connection and run on all the software on the PC. And once everything is stable and the software gets optimized, it can be transferred to the embedded platform. And once that happens, the API to the SDK remains the same. So basically no changes have to be made on that front. You just have to compile the SDK for the embedded platform and everything stays the same. So there's a consistent development throughout all the I guess product development cycles, like prototyping, application development, and then deployment onto the, I guess, final hardware configuration or final product. And since the SDK is open source, we are hosting it on a GitHub repo where you can find code, examples, documentation, user guides, SD card images for the supported embedded platforms, releases for the code and the tools. We are using the CMake build and install infrastructure, so that's available on GitHub, continuous integration. We handle issues over there, and we're also using GitHub for project tracking. So basically, everything that's needed is available on GitHub, and we are trying to provide a very good experience to our users and to give them everything they need to get up and running quickly in evaluating the solutions, and then further on developing their own systems. So the Python API is actually a layer that sits on top of the C++ SDK implementation. So the entire code in the SDK is written in C++, and we have this Python API that sits on top of it and basically implements the entire functionality of the SDK. So we have a like one-to-one mapping between the C++ API and the Python API. So this diagram kind of shows the different blocks which sit at the different SDK levels. So for example, in the low-level API, we have direct access to the depth sensors, to any storage that might be on the system. So for example, all these systems, they require like an EEPROM or some NVRAM to store the calibration data for the depth sensor. It also has temperature sensors for compensating the measurements based on the system's temperature. And it's also the high-level API, which includes things like frames or the camera or something which we call a system, which is a component that helps discover cameras and configure the cameras based on where the SDK is running, either on a PC or an embedded system. So in Python, we actually implement everything that's exposed in these APIs in C++. And in order to do that, we have been using PyBind 11. All the bindings are available in a single file. So we have about 300 lines of code in that file. And there are quite a few useful features that we have used from PyBind. Is like functions accepting or returning custom data structures per value, reference, or pointer. We are using smart pointers a lot, so that was a feature that was really useful. One other thing that we are doing in the SDK is that we are returning like buffers of data, but not as a return into a function, but as a pointer, which is taken as a parameter by that function. So that's a pretty nice feature that was available in PyBind 11 that allowed us to keep the same type of implementation between the C++ and the Python code. We are using STL data structures, single and multiple inheritance, custom operators, and enumerations. So these are quite a few useful features that we did use when implementing the Python bindings for our SDK. And here are just a few examples of how we did things. So for example, this is how like a status class was implemented in Python. So basically all the elements of this class were translated into Python arguments that will be used further on in the code. The other example is a class implementation. So here on the left we have the C++ implementation, and here on the right we have the Python binding. And what's interesting here is that, so for example, there are these functions like initialize, start, stop, that don't really receive any, that don't have any parameters. And in order to implement the binding for them, we just had to do this define, and that was basically it. And there are more, I guess, complex functions like setMode, which receive 2 parameters, and they have a different way of being implemented in the Python binding. But again, very simple. So it's basically just 2 lines of code, or maybe just 1 line of code, just because of formatting. And another more complicated function is like the get available modes, which returns a list of or a vector of strings, which is the modes that the camera supports. So this has like a more extended implementation, but again, just a few lines of code. So basically, using PyBind 11, it was really easy to implement the bindings, the Python bindings, starting from the C code with, I guess, minimum overhead. And here's again a code example showing all the steps to, I guess, initialize a camera, configure it, and request a frame from it. So here on the left we have the C code, and here on the right we have the Python code. And basically, you can see from here that there's like a one-to-one mapping between the different function calls. And here you can see what I was talking about earlier in terms of returning like buffers of values. So for example, this get available modes function returns a list of modes, and this is the way that it was implemented in Python in order to keep a similar implementation to C++. And on GitHub, we do have example applications for Python, starting from the like very simple ones where we're just configuring the camera and streaming data, to more complicated ones like DNN object detection or displaying point clouds. And what's nice about the Python bindings is that they provide a way to interface with other image processing libraries like OpenCV or Open3D. And basically, by having the Python bindings, it was really easy to use functionalities from these libraries or to run already existing examples in those libraries. And next, I'm just going to go into some a bit more advanced machine vision applications using Python and using different, I guess, tools and frameworks provided by processor manufacturers like NVIDIA or Rockchip or NXP. So in this case, I'm going to focus mostly on NVIDIA. And the first example I'm going to show is about detecting people. And in order to do that, we have used a library which is called DetectNet, which is actually a new example neural network model architecture in digits, which is the NVIDIA Deep Learning GPU training system. So a DetectNet object accepts an image as input and outputs a list of coordinates on detected bounding boxes. And there's also some clustering, which is implemented in a Python function that is invoked in Caffe through the Python layers interface. So basically, DetectNet is based on Caffe, and Caffe has this feature which is called Python layers, where custom functions can be implemented in Python and ran as part of the AI model. So what's nice about DetectNet is that it makes use of NVIDIA's TensorRT, which is optimizing the AI models for the NVIDIA GPUs for efficient operation and basically being able to run in real time the applications. And this kind of shows the architecture and what's going on over there. So we have the time of flight camera, which connects to an NVIDIA Xavier AGX platform. We have been using the ROS bindings for the time of flight camera in order to get data from it, and also the ROS Pi client, which basically allows us to interface a Python application with a ROS processing chain. And the chain is kind of highlighted here. So we have all these blue boxes, which are implemented as, I guess, blocks in ROS, in C++, or some or even Python. And we have the AI object detection, which interfaces with those blocks through ROS-Pi. So the cool thing about this is that we can use Python in the, I guess, development prototyping stage and do all the development in Python and interface with I guess, optimized processing blocks. And once everything is proven to run perfectly, and we can see the results in real time by doing that, then the Python implementation, if necessary, can be transferred into a C++ implementation, which is actually optimized for that specific platform and that specific application. Another example is pose estimation. So this is based on the NVIDIA TRT pose open source implementation, which has pre-trained models for human pose estimation and also training scripts to train on any key point test data in MS COCO format. Again, TRT pose is completely based on Python. It's available online on GitHub, so anyone can use it. And by having the Python bindings, it was really easy to interface with this library and run the algorithm. And here in this video, we can see the algorithm running on the IR data that's coming from the camera. And so the 3D camera actually outputs two video streams. One is like an IR stream, and the other one is the depth stream. And they are perfectly synchronized in space and time. And by detecting the human pose points on the 2D image, then we can directly translate them onto the 3D image and get the depth or the XYZ coordinates for those points. So we also get the depth information, and by doing that, there are many things that can be detected, like gestures, like movement intention, and things like that. So that's kind of the added value of having the 3D data in this case. So all this is running on an NVIDIA Xavier NX. Again, it's using a similar structure as the people detection application, which I presented before. So the TRT pose algorithm is using stuff like PyTorch or Torch Vision in its implementation. And again, we are using NumPy and ROSPy as additional packages in order to implement this application. And the last one I want to talk about, the last application I want to talk about, is volumetric estimation from time-of-flight data. So basically, this was done using a technique which computes the normals in each point of the image. And after having the normals, we are obtaining the intersecting lines of the perpendicular planes by using an algorithm which is called the SOMAR algorithm. And this algorithm kind of gives us these red lines here, which are the intersections of the planes. And by having those lines, we can compute the dimensions of the box in real time. So this is a really good use case for a 3D camera, because it allows us to compute, not just detect where a box is in an image, but also compute its dimensions and its volume. So in this case, we didn't use ROS. We just used the analog devices time-of-flight SDK, Python API, and NumPy. And here you can see an image with two boxes, and the implementation was able to detect both of them and to compute their corresponding volumes. So to conclude, there are just a few key takeaways that I want to mention. So one of them is that 3D sensors enable machines to have high resolution 2D and 3D perception, which is really useful in many applications like autonomous robots, logistics, and all the things I talked about in the beginning. And it alleviates the need of having additional sensors besides the vision sensor, because vision and depth sensing is enabled in the same sensor. Alongside our hardware offering, at Analog Devices, we provide the time-of-flight SDK, which comes with a fully featured Python API. And the nice thing about the Python API is that it enables an easy transition between prototyping and optimized implementations. So it's just like the examples I showed before with the raw SciPy interfaces, where we can have the Python code running as a block there, and once everything is fully proven, we can go to the optimized implementation and switch back and forth until I guess we are satisfied with the results. And here are a few resources. So it's on nlog.com/TOF, where you can find more information about the time-of-flight solutions that ADI is providing. Is the link to the GitHub repo for the time-of-flight SDK. Engineer Zone, which is a forum where ADI engineers answer questions about different ADI products and different ADI systems. And there's also a link to a paper which is called CNN-based TOF image processing, which is included in the SciPy 2021 proceedings. So with that, I want to thank you for attending this session. Hopefully it was useful and gave you some insights on what 3D depth sensing is and what are the different things that can be done with the Python bindings that we are providing on top of our open source SDK. Thank you.
Great, thank you, Andre. Does we have about 3 minutes left for any questions that anyone might have? You can post it in the Q&A section, or you can raise your hand to be taken on stage. Okay, well, I do have a question. So those examples you showed earlier, were they all done, like the processing, was it all done in real time?
Yes. So the processing was done in real time. So basically, we ran all the examples on NVIDIA platforms, and one of the reasons why we used the examples from NVIDIA is that they have so all their models, they are done in TensorFlow, and they have integration with TensorRT, which is basically an optimized implementation of the model, which can run in real time on an NVIDIA SoC.
Great, that's super cool. I guess does anyone have questions? If not, then thank you for presenting, super cool. Our next session will be in about, I guess, 7 minutes now. So thank you all for attending.